So as we said, we have one more proposition that we need to prove. This is the last proposition in section 2.c of Axler, which goes as follows. Let V be a finite dimensional vector space. And let's say we have two subspaces, V1 and V2, subspaces of V. Then the dimension of V1 plus V2 is equal to the dimension of V1 plus the dimension of V2 minus the dimension of V1 intersect V2. And this should seem somewhat plausible because it kind of sounds like the inclusion-exclusion principle, right? I'm saying something like the total amount of stuff in their sum is the stuff in one plus the stuff in the other minus the stuff that I double counted. And in that sense, this is a perfectly okay way to think, and we can use it to prove this fact, provided we are careful with what we mean by the stuff. So how does a proof of this go? We start with V1 intersect V2, and we pick a basis. And why don't we give this basis a name? How about we call it V1 through Vm? Since it's a basis, of course, this tells me that the dimension of V1 intersect V2 is equal to m. On the other hand, since V1 intersect V2 sits inside both V1 and V2, I can extend this basis of V1 by adding in, how about U1 through U, Axler uses notation J, so how about that? U1 through Uj. And that tells me then that the dimension of V1 will be M plus J. Same trick applied to V2. Let's add in this time W1 through WK so that the dimension of V2 is equal to M plus K. Now, under this setup then, what would this tell me? This would tell me, like if I look at the theorem that I'm trying to prove, I have, let me just write it again since we've kind of scrolled down a little bit. Well, for V1, I have M plus J. For V2, I have M plus K. And then I have minus M. So in other words, I cancel one of these M's and I have M plus J plus K. And that should make some amount of sense because what this says is that what I should be trying to do then is to consider the set of all of my V1s through VMs, all of my U1s through UJs, and W1 through WK. Well, if this is a basis, we're done, right? Because this has M plus J plus K things in it. And so if this is in fact a basis, let's call this B for basis. If B is a basis for V1 plus V2, then we're done. And actually, we're halfway there off the bat. Why? Being a basis means two things: linear independence and spanning. But of course this is spanning because V's and U's span V1 V's and W's span V2, and V1 plus V2 is, by definition, the stuff that you can make using V1 and V2 respectively. So, therefore, the B spans V1 plus V2. The interesting part of the proof then is to prove that it's linearly independent. And so you'll have to pardon my algebra just a little bit here, slightly tedious. We need to look at equations of the form sum all of my v's. Hold on. What letters have I used already? M, J, and K. I guess I'll just use the letter I, right? The I. How do I even do that? They're different lengths. AI. I'll just write it out. I'm not going to think about notation. A1 V1 plus A2 V2 and so on up to what we said, M? Yeah, AM VM plus B1 U1 up to BJ, we said, UJ plus C1 W1 up to CK WK. I want to set this equal to 0. This is the kind of thing that I want to study, and I need to prove to see linear independence means all A's, B's, and C's have to be 0. Okay, this looks like it's a lot, and it's not a lot, but the proof is not as bad as we think. It's just that the notation is kind of ugly because there's 3 kinds of things running around. So the first thing I'm going to do is I'm going to take all the C's and just put them on one side of this equation by themselves. We push everything else to the other side. So I got A1, V1, and so on up to AM, VM. And then also B1, U1 up to BJ, UJ. We push all those things to the other side. Why am I doing this? Because if I write this in this way, then what this shows me is these things were all in V1 intersect V2. These things were all specifically in V1. And so therefore, this linear combination is also in V1 because everything in sight is in V1. Okay. Sorry, I'm just thinking about that. I feel like I had an idea for how to finish this and then maybe I forgot. Let's have a quick think. I'm trying to sort of leverage this, and I see. So the W's were also in V2 by definition, right? So that means that this whole sum is also in V2. And so that means this thing lives in V1 plus V1 intersect V2. To be clear, I'm not saying the individual C, I, W, I vectors live in V1 intersect V2, but I am saying that the sum lives in V1 intersect V2. On the other hand, the V's are a basis for V1 intersect V2. So since the V's are a basis, it must be then that this expression C1W1 up to CKWK must be some combination of the V's. Of course, it's some different combination, right? But you see, now we're ready to finish this because the issue is that the V's and the W's were linearly independent. We selected the W's to be a linearly independent thing that extends from V1 intersect V2 up to all of whichever one of the V's makes my statement correct. And so by pushing everything to one side, I obtain a linear equation of linearly independent things, which is equal to 0. So therefore, all C's and D's equal 0. And this is what finishes us off, because I don't actually care about the D's at all. I care about the C's. Since the C's are all 0, this all drops out. And what's left are the A's and B's. But you see, the magic is the A's and the B's, right? The U's were selected as a basis extending the V's to all of their vector space. And so this is a basis for that vector space, and it's equal to 0. In particular, since it's a basis, this equation has no non-trivial solutions. So therefore, all the A's and B's are also 0. And what we wanted was that conclusion, which we got. Okay, I want to wrap this up, but I want to quickly pause before we conclude to say that while this formula looks like inclusion-exclusion, it's actually not true in general. And what I mean by in general is a little bit suspicious. Like, there are situations where it's true and there are situations where it's not true if you try to do with more subspaces. In other words, we could ask ourselves, like, what would we expect to see for the dimension of a triple sum? You might think that it should be something like the sum of the individual dimensions minus the intersections plus the triple intersection. This is what you might expect from the inclusion-exclusion. But it turns out this isn't true in general. There's situations where it's true. And maybe I'll give you guys a homework problem, either officially or unofficially, to find a situation where it's true. But let's just start by dispelling the idea that this has to be true in general. Let's take, for the big vector space, just the normal plane. And then, right, so here's V. Here's V1. Here's V2, right? The X and Y axis, or the span of E1, the span of E2. And then here's a third thing, V3, another one-dimensional space, the span of E1 plus E2. Well, V1 plus V2 plus V3 is just equal to V, right? Because V1 and V2 were already a basis, or sorry, E1 and E2 were already a basis. So V1 plus V2 was already equal to the whole space V. And so the V3 adds nothing. So in this equation, that first term is 2. These next terms, these are all 1, right? They're all one-dimensional spaces. The intersections, every pair intersects only in the 0 vector, which is 0-dimensional. So then we get minus 0, minus 0, minus 0, plus the triple intersection, which again is just 0. So that equation would tell me that 2 equals 3. So it's not true. And I think a lot of people don't know this. In fact, I know at a time a lot of people didn't know this because I first learned this from on the internet on a collection of facts that are, I forget what it was called. It was something like theorems that are so crazy, or what was it? Hold on. Theorems that you've never heard of because they're false, of being the joke that they're not actually theorems. And this was one of those things that was listed as a quote theorem unquote, which isn't true. And it comes from this idea of doing inclusion exclusion to see the simple case with 2 vector spaces. I think it's a worthwhile exercise to figure out where in the proof that this breaks, like to review this and like figure out why this logic doesn't work. But I think that's probably too much for just one of our homework. So I'm not going to make you do that. Also, it's a little bit more of an advanced kind of, how do you say, like breaking a specific proof is a more subtle thing than just writing a straightforward proof. So I think that it's reasonable to find that to be a greater deal of challenge than our regular homework problems. In any case, that's all for me. We are halfway through chapter 2 now, which is cool and good. And so there will be a quiz after this that deals with some of the computational aspects of what we've been talking about, as well as some homework problems that will continue to build on these themes. So that's all for me. And I will see you guys in the next one for chapter 3. See you guys soon. Or sorry, not chapter 3, the back half of chapter 2. What was I just saying? Got to listen to myself. Take care, friends.